My guest today again is Ian Plimer. And Ian, what's new with your book, Climate Change, The Facts, 2025?
Well, this is a series of books that's put out by the Institute of Public Affairs. And that is a free market think tank that's been operating since 1943. And they're fairly active in promoting free markets. They're fairly active in being anti-woke, pro-freedom. And one of the other areas they're very active in is looking at climate. And this is one of a sequence of books, I think there've been about 3 or 4 of them now, called Climate Change, The Facts. And it's basically the latest information on climate change and the latest information which really does question the popular paradigm, and that is that humans have anything to do whatsoever with climate change. And that area is fleshed out in the book.
Excellent. Yeah, I spent quite a bit of time reading it today. There's 14 chapters in there, lots of different authors, lots of people from Australia contributed, correct?
Yes, well, the Institute of Public Affairs is a Melbourne-based think tank, so there are some Australians there, but there is a summary of Will Happer's talks that he gave in tours of Australia last year, and those are always very enlightening and very invigorating. So that's done by one of the editors who attended these talks.
I'd like to start by talking about your chapter. Your chapter is 4 on the geology of climate change. I thought it was just very fascinating to go through it. Do you want to talk about that?
Well, very few people have a knowledge of geology. And geology tells us about the past. It tells us the history of the rich 4,567 million years that we've had on planet Earth. And the one thing we do see are massive climate changes. We've had a couple of periods of time in the past when the planet was covered with ice. And we had ice at the equator, at sea level, and it was many kilometres thick. So that poses some questions. Well, what drove this great climate change? And even more so, how did we get out of the snowball Earth? And so if we're looking at modern warming, we've got to be able to look at what's happened with past warmings and how these past warmings have been natural. So what component of today's warming is natural and what component is actually from human activity? So I look at the past climates. I look at the fact that for more than 80% of time, the Earth has been a warm, wet greenhouse planet. For more than 80% of time, carbon dioxide has been a major gas in the atmosphere. Now it's a trace gas. And ice is a very rare rock. It has been on planet Earth for less than 20% of time. And we are currently in an ice age. And the best thing that can happen in an ice age is to have some natural warming. And I look at the cycles of climate, how we've got cycles driven by where the continents are, driven by what's happening in the galaxy, driven by the Earth's orbit, driven by oceanic cycles, driven by cycles of the sun. And we can see that within the last, say, 50 million years, we've had a cooling trend. Well, within that cooling trend, we've had slightly warmer periods and slightly cooler periods, but we've been cooling for a long period of time. We've been in an ice age for the last 34 million years. And during this period of time, we've had spikes of warming and spikes of cooling. We know this from historical times. From historical times, we had the Minoan warming, and then we had cold times. Then we had the Roman warming, and then we had the cold times of the Dark Ages. Then we had the medieval warming. Then we had the cold times of the Little Ice Age. And of course, the next cycle after that cool period would obviously be warming. And that's what we're in now. So I look at the cycles and I look at what we've learned from the past. And what we've learned from the past is one really important parameter. And that is that we see no evidence from the past that carbon dioxide drives warming. Absolutely no evidence whatsoever. And so the whole popular paradigm that this plant food, which most of it is emitted by the oceans, but this plant food drives global warming, we see no evidence for that. Now, others in the book have got into various aspects of carbon dioxide. Tom Quirk, who's a carbon dioxide chemist, has a chapter there. Will Happer refers to carbon dioxide and its role in climate, which he argues is infinitesimally small and possibly immeasurable.
One thing that jumps out at me as I read your stuff and the other chapters is the more you learn about climate, just the more complicated it is. Did you agree with that? That there's so many different cycles?
Very much so. Very much so.
Yeah.
And those people who are wanting to frighten us witless are looking at one parameter, and that is carbon dioxide. And they're looking at humans emitting traces of a trace gas into the atmosphere, an atmosphere which in the past had hundreds to thousands of times more carbon dioxide in it than now. And during that period when it had very high carbon dioxide, we actually had global cooling, we had ice ages, we had snowball Earth. So what I tried to do in my chapter and what the others try to do is to show that this is a very, very complex phenomenon, and climate change cannot be related to traces of a trace gas, which is plant food, that humans might emit. It's far more complicated than that. And if you ignore all the other parameters, then you come up with an illogical conclusion. And that's what we've come up with.
So one thing you start out with in your chapter is the ocean floor itself is not just static, that it is changing. There's tectonic things going on, and there's currents are maybe getting diverted because ridges are growing or sinking or whatever. Just a lot is going on under the ocean. Is that right?
Well, we don't see it. And
Right.
it's very hard to measure it. Very few measuring stations are on the ocean floor. And it is the oceans that drive the weather. It is the oceans that are very important in climate because water has a very high heat capacity. You can hold a lot more heat in water than you can in the air. And I'll give you an example. If you run a hot bath, then the air in the bathroom gets warm. If you run a cold bath and put a radiator in the bathroom, then the water doesn't get warm. So it shows you that the air has a very, very low heat capacity. Water has a high heat capacity. So when you move water around, you are actually changing the balance of heat on the surface of the ocean. This is mainly done by water currents. We also have a process of evaporation, which involves heat, and a process of precipitation of rain and snow, which involves heat. So water is the key component. So if we change the shape of the ocean floor, such as putting in a dirty big volcano on the floor of the ocean, we will divert ocean currents that are carrying heat. And so we change the weather and ultimately change the climate. If we change the position of the continent, something we've known about for 50 years or so, if we change the position of the continents, we're changing the way in which ocean water moves. And it may well get diverted by a continent appearing here, there, or everywhere. And this is what's happening at present with Antarctica. We are not having warm water from the equatorial areas come into the polar areas. The continent of Antarctica has got a circumpolar current that stops warm water coming there. The continent that sits at the South Pole is glaciated. And until we break up that continent, a process which is happening and has happened for 100 million years, until we break up that continent, then the oceans will drive the fact that Antarctica has an ice sheet. So it is the oceans that are the most important.
We all agree there's not enough geologic heat that's going to make cause the oceans to heat up rapidly. But in certain spots, it is changing ocean currents, so that in certain spots, the geologic heat is very important, even as far as maybe kicking off El Niños. Does that sound right?
Yes, there's some very interesting seismological evidence showing that when we get swarms of earthquakes in the mid-ocean ridges, then we have that followed by an El Nino. Now, why do you get swarms of earthquakes? Well, this is because you've got molten rock rising and pushing aside the rocks so that molten rock can get to the surface. The mid-ocean ridges is where we're pulling apart the oceans. This is where we're getting decompression deep in the planet. And we can make molten rock by decompressing a rock that's under high temperature and pressure. So we've got some really good experimental evidence and very good measurements showing that maybe there's something more going on in the oceans than we think. And there's a strong suspicion amongst volcanological circles that the seismic activity, of course, the resultant volcanic activity on the seafloor, might be driving the El Nino-La Nina cycle. And the jury's still out, but these are very fascinating ideas. Now, what this means is that science is never settled. What this means is that we're constantly finding out new information. And if we do put a volcanic rock in a mid-ocean ridge onto the seafloor, then that volcanic rock is a basalt. It's about 1100 degrees Celsius when it's molten. Seafloor water is at 2 degrees Celsius. So you transfer heat from this basalt into the seafloor waters. Those seafloor waters actually heat up and they rise and become a surface blob of warm water. Now, there's been quite a bit of work done by a Hong Kong scientist, Wis Yim, on this, and Wis has been able to show us that there's a very close relationship between submarine volcanicity and the El Nino-La Nina cycle. We need more data. We need more time to gather that data, but science is not settled. It never is. If it was settled, then those people who are promoting climate science and wanting to tell us that the world's going to end and the science is settled, well, we should stop funding them. They've done their work. The science is settled. Go away. Go and become a barista.
Great advice. There's a whole other chapter on volcanism in this book. And another point that's made is we can't predict it, right? That there's been a lot of just surprise volcanoes. They've been dormant for enormous lengths of time, and all of a sudden they explode. Do you think we're making any progress there, that we're going to be able to figure out ahead of time which one's going to blow next?
There's a French scientist who worked in the Western Pacific called Claude Bleu, and he was able to look at very, very deep earthquakes and was able to predict when we're going to get massive volcanic eruptions. Now, that work was never followed up. He probably saved tens of thousands of lives in the New Hebrides and the Solomon Islands by his work. So we have a hint of some scientific work suggesting that we might be able to predict volcanic eruptions. If you are living on a volcano, as many people in, say, Indonesia do, there are monitoring stations. These monitoring stations measure the temperature of gases and water coming out of the volcano. They measure the slope of the land. They measure the magnetic field. They measure the gravity. And you can predict an eruption that might occur in 2 or 3 days' time. And that's about as good as you can get. But you cannot predict an eruption that might be out in the ocean, such as the recent Tongan eruptions, which put a huge amount of seawater into the stratosphere. You cannot predict those. And that, of course, is one of the great areas of science that needs to be explored some more. The same with earthquakes. There've been 1,000 years of people trying to predict earthquakes. Probably the best indication is when you have animals get quite agitated. That may well be due to electrical currents where you're bending and breaking minerals before you actually get a fault zone and a shock wave. So there's a lot of work to be done on trying to predict volcanoes and, of course, trying to predict earthquakes. But by not being able to predict them, then we have this unknown factor in climate that one volcano can ruin your whole day. One massive volcano can actually change the Earth's climate. We've seen it in the past. We've seen it certainly change the weather, such as Tambora in 1815, such as Krakatoa in 1883, such as Santorini in 1600 BC. We know that volcanoes can actually change the weather quite considerably. We also know from, and I think the date 1783, a volcano in Iceland that erupted and produced a huge amount of sulfurous gases into the atmosphere. This was observed by Benjamin Franklin, who quite correctly said this is due to a volcano, but people in Europe were dying of respiratory diseases. Now, if we could predict such events, then we would save a lot of lives on planet Earth. We can't, People are trying, but it is absolutely vital in any climate projections, 100 years or 200 years into the future, that you actually put into the equation what volcanoes are going to erupt and where. Because a polar volcano, such as in Antarctica or such as in Iceland, has a very, very different effect on climate than an equatorial volcano. So again, that's a work in progress.
So I think I saw somewhere in the book that they were saying that maybe a Mount Pinatubo-sized volcano might occur maybe 3 out of every 4 centuries, maybe something like that. But there was one called Mount Toba. I'm looking here, 70,000 years ago. That was 1,000 times as big as Pinatubo, maybe, and that caused a 1,000-year cooling episode. So we just don't know, I guess. And you made the point that just the size of the volcano and the location doesn't necessarily tell us what will be emitted, right? Or how high in the air it's going to go.
You mentioned Toba, and Toba about 70,000 years ago. Now, that's in Indonesia, so it's an equatorial volcano. And Toba was a supervolcano, like the ones that you have at Yellowstone, like the ones in Kamchatka, like the ones in the Taupo volcanic zone of New Zealand. These supervolcanoes are very different from a volcano like Krakatoa. Krakatoa, when it erupted, it put 30 cubic kilometers of rock, which was pummeled into dust, into the atmosphere. It put also some sulfur gases into the atmosphere. Now, 30 cubic kilometers of rock sounds a lot. But when we look at supervolcanoes, like some of those in your Yellowstone area, some of those in Taupo in New Zealand, they put out 10,000 cubic kilometers of rock, which is broken up into dust. When Toba erupted, the measurements of the thickness of the ash layer suggest that about 3,000 cubic kilometers of rock was ground up into dust and blasted into the atmosphere. Now, that had a profound effect on the planet. Firstly, we saw the extinction of a number of equatorial species. Around about that time, we had the extinction of 3 of the 4 species of humans. We, as Homo sapiens, went down to about 4,000 breeding pairs. We very nearly became extinct. One volcano could have sent us out backwards, could have sent us extinct. We know that some volcanoes change history, such as the Santorini volcano of 1600 BC, and that led to the destruction of the Minoan Empire and the rise of the Mycenaeans and the Athenians. So Toba is a very important eruption because that was during a natural cooling cycle where we'd started cooling 116,000 years ago, then we started warming about 14,000 years ago. That occurred 70,000 years ago. It occurred during a cooling cycle. It sped up the cooling, and it led to the dispersal of humans from tropical areas into more temperate areas. That's perhaps when we had the first influx of Aboriginal people into Australia 70,000 years ago. And there's some scant evidence around, but it may well be tied into Toba. So that is a supervolcano. Supervolcanoes can change the climate and change the weather, and they can do it for a very long period of time. Now, if you want to pick a period in historical time when it was the worst possible time to be alive, it would have been at the beginning of the Dark Ages, about 535 to 537 AD. And there we had volcanoes in Central America, Papua New Guinea, and Indonesia all explode within a 2-year period. The equatorial atmosphere, in other words, both hemispheres, had a huge amount of dust, a huge amount of sulfurous compounds. If you wanted to cough yourself to death, if you wanted to have your eyes bleeding and your tongue raw, that was a period of time to live. If you wanted to have crop failure, that was a period of time to live. If you wanted to have air so thick with dust that it was almost permanently dark, that was a time to live. And no wonder this was called the Dark Ages, because it was bloody well dark.
The cold times have always been bad times, and the warm times have always been good. Is there any exceptions to that rule where it's gotten too warm for humans? There isn't.
No. We know from measurement of deaths of about 34 million people that if you're going to have a climate-related death, 90% of those who die due to a climate event die during cold times. During warm times, yes, some people, especially people my age and older, will expire because it's hot. And some parts of the world, you will get prolonged periods of time when it's 45, 50 degrees Celsius. We see that currently in parts of the Mediterranean, Saudi Arabia, parts of Central Australia. We have very, very hot times, and they kill people. Now, what we find in the cold times is the deaths are due to freezing, they're due to a lack of food, they're due to basically the body being overstressed. We have a natural thermostat on planet Earth, and that is called water. And so if it warms up, we evaporate more water. That's a process that requires energy. So you're taking energy from the ground or from the air and cooling it to evaporate that water, and then you precipitate that water. So the planet's atmosphere, with its water vapor, operates like a natural air conditioner. And once there's water vapor in the air, there is a maximum temperature you can reach. And in tropical humid areas, the maximum temperature is about 35. In areas which are temperate, where there's very low humidity, the maximum is about 55. And I've experienced that in Saudi Arabia, and it's baking hot, but it's not as uncomfortable as 35 or 38 when it's very, very humid. So we know from medical records, we know from the past, and we know from the records of the rate of evolution that it's cold climates that kill, warm climates lead to a massive spurt in species diversity and a massive increase in vegetation and in plant life and in, of course, animal life.
Do you get any sense that within the scientific community, they understand that warm times have been good times? Do people not really understand that, and that's why there's so much alarmism?
I think in order to get funded and to get the publicity as a scientist, you need to be alarmist. And so people might, on one hand, be thinking something, but on the other hand, are saying something. And you see this often when prominent climate scientists retire and they say, well, you know, folks, in order to survive in the highly competitive world of winning research grants, I really had to toe the party line. So it is very, very basic physics, and some of it is dealt with in this book, where one of the authors is dealing with evaporation and precipitation and the amount of energy that's transformed. So I think that's quite well understood. It's certainly been understood for 100 years, and why it is not understood now would be beyond me, unless people are trying to survive in that highly competitive world of research grants.
Do you think there's any dynamic in climate science where people in their 20s, they got into climate science because they wanted to save the world, and they're all in still on the alarmism? Or do you see anything as the pendulum's shifting at all, where people are starting to figure out that there are other drivers than CO2? What do you think is happening?
Well, I think you're quite right. I think many people get into environmental science, whatever that is, or get into climate science, whatever that is, because they're wanting to save the world. Now, in both of these areas, you have to have a deep understanding of geology, biology, physics, and chemistry before you can start to talk about how the atmosphere works and how you transfer heat around the atmosphere to give you climate, or in the case of the environment, how you transfer materials in the waterways, in our seas, and in our soils before you can understand what's happening. So I think a lot of younger people do want to save the planet. The problem is that having an ideology and wanting to save the planet is very different from having the knowledge to be able to put saving that planet into practice. And I think as scientists get a bit older, they realise that systems are very complex. Systems may or may not have interrelated parameters. Systems may be random. And the prediction becomes an art rather than a science.
So for you as a geologist, I'm curious, you must run into or talk to quite a few real geologists. Is there alarmism at all is there anybody who knows all this stuff about climate cycles and they still are alarmist? I can't imagine how that could happen.
Well, you can count on a sawmiller's hand the number of geologists that think that humans drive climate change. And I mix very broadly in geological circles, in academic circles, in the circles of those people who actually find and mine mineral deposits. You're really pushing it to find someone who actually, and I use the word believes that humans drive climate change, because belief is a word of politics and it's a word of religion, but it's not a word of science. And geologists, like other scientists, try to use evidence to underpin their conclusions. So in my profession, which is a very minor profession, there are very, very few people who are geologists. We are basically those who provide the commodities for the world. You would be pushing it. Now, this is especially so with petroleum geologists, and petroleum geologists are looking at sea level changes. It's extremely important in petroleum geology, also important in coal geology. And in the 1960s, a geologist from Exxon, Peter Vail, constructed some sea level curves for the last few 100 million years. These are extremely accurate, and these sea level curves are based on what sort of sediment is deposited, how quickly that sediment was deposited, whether that sediment was a marine or terrestrial sediment, what are the fossilized life forms in those sediments. And that has been used for a very long period of time in a practical sense, and that is to find oil and gas. So not only have we got a construction of the past, it actually works. And that's how we're able to find oil and, to a lesser degree, coal, because we understand what sea level was doing. So geologists have seen sea level go up and down. I can go to outcrops, and there's an area that I used to take students to up in the North Flinders Ranges of South Australia, where you can look at rocks that are 700 million years old, and you can work out that sea level was rising at that period of time. It's very easy to do. So we've had these concepts in geology for over 100 years. And because so few people know anything about geology, it gets ignored.
I think somewhere in the book it mentions that sea levels may have been a couple meters higher a few thousand years ago on Earth. I'm curious, for the whole of human history, how high did sea levels get? How much higher than current is the highest that humans may have experienced?
Well, the first part of your question is yes, we did have higher sea levels in the Holocene optimum, and that was about 4,000 to 8,000 years ago, and it was about 2 meters higher. During the last interglacial, between 116,000 and 128,000 years ago, sea level was about 7 meters higher than now. If we go right back through geological time, we find that sea level was probably about 50 meters to 80 meters higher than now over most of geological time. Now, that's a hard calculation to do because you don't know the depth of the ocean. And if you have an ocean trench form, a lot of that will be filled with water. And so sea level elsewhere around the world will drop. If you put a large body of molten rock on the sea floor, that will displace seawater and sea level will rise. So it is very, very hard to calculate what's happened in the past. But because we are in an ice age, because we have hundreds of millions of years of very good records based on the sea level curves of what sea level was doing, we can fairly confidently say that for the bulk of time, sea level was higher than now, tens of meters up to maybe 80 meters higher than now.
And maybe I missed it, but just the entire average floor of the Atlantic Ocean, for example, 50 million years ago, can we tell if that has moved up and down, or does that make any sense, that the floor would move up or down over that much time? The
floor of the oceans does move up and down. It also moves sideways. So the oceans have been getting bigger, and this is first recognized in the 1960s. They get pulled apart at the mid-ocean ridges, and at the edge of the oceans, we push the ocean floor beneath the continents. And so beneath the Andes, we are pushing some of the Pacific Ocean floor underneath the Andes, and we're pushing wet basalt and wet ocean floor sediments beneath the Andes to a great depth at high pressure and high temperature. So immediately the scientists will say, I wonder if I can repeat that. And this has been done. We have actually been able to create the rock andesite, which comes from the Andes, by partially melting basalt or basalt plus a bit of ocean floor sediment at high temperature and pressure with a bit of water around. And we've been able to do that. So these theories are substantiated by significant experiments, which then support our geophysical and topographic measurements, showing that the ocean floor is expanding, but also going up and down a little bit. Now, we see that in places like Ephesus in Western Anatolia in Turkey. Ephesus is a port city. It's mentioned in the Bible. And I've been to the port of Ephesus, which is inland and above sea level. I've also been to the city of Lydia, and Lydia is where King Dryas first minted gold coins. I've been down the main street of Lydia in a yacht. So sea levels constantly go up and down, land levels constantly go up and down, oceans are constantly expanding and contracting. We are forming new oceans, such as in the Red Sea right now, and we're destroying old oceans. So the planet is dynamic. Now, if everything on the planet is dynamic, why isn't climate? Why are we told that the climate was static until such time as we dreadful, sinful humans came along and started to emit plant food? So the whole thinking and that sort of logic goes back to the ancient Greeks 2,500 years ago. That whole thinking process is ignored. We are being frightened witless about plant food being emitted into the atmosphere. And one of the reasons for that, I think, is that plant food we emit comes from industry. It comes from burning fossil fuels. It comes from making fertilizers. It comes from making cement. And because we're in a process of political deindustrialization, then it's a very, very easy gas to attack. The most important greenhouse gas in the atmosphere is water vapor. Now, if someone said, oh, we've got to ban water vapor, you'd be locked up. Well, I say the same argument applies to carbon dioxide. If you want to ban plant food, if you want to try to interfere with the carbon cycle, you should be locked up.
So I have another question about Antarctica. Am I right in saying that if you were to drill all the way down at the South Pole and got to land under the ice, that there are signs of life there, that it was warm enough for life there at some point? But is that because of continental drift and whatever is at the South Pole right now, the dirt that's there was far away when there was life? Or was it ever warm enough on Earth for 90 degrees south for there to be life living at 90 degrees south?
Well, there's a couple of things. We have some deep drill holes in Antarctica through the ice, and the ice in Antarctica, as well as in Greenland, is held in basins. Now, that ice moves uphill before it moves downhill in glaciers to calve into the sea. So if global warming is meant to be causing the melting of ice, how come the ice is moving uphill? There's got to be different processes involved. Now, we know these processes well, and that's ice recrystallizes, and that's part of the process of moving. Ice at the head of the glacier is very fine-grained crystals. At the toe of the glacier, it's quite coarse-grained crystals. Ice moves by totally recrystallizing. So our drill holes into the ice show us that the ice in Antarctica is in a basin. We can, from chemical fingerprints in that ice, work out changes in climate which are related to the orbit. And then we have, beneath that, we have rocks that are on Antarctica. These are exposed in many places. And we see that in Antarctica, we once had cool climates to give us the coal deposits that we have in Antarctica. Once had warmer climates to give us some of the deposits, fossil deposits we have in Antarctica. And we see that Antarctica was very little different from southern South America or Australia or India or South Africa. So these continents were once joined and they started to pull apart, and Antarctica has parked itself over the South Pole for more than 100 million years. And that has driven our climates. And what has happened is we've had this arc of ancient fossilized material carried and parked itself over the South Pole. And what's happening in Antarctica is that it did break up. We had India, Australia, and South America and South Africa pull away. A little bit later, 34 million years ago, we had South America pull away. And we're still getting the breakup of Antarctica because we see about 150 zones of high geothermal gradient where we've got volcanoes. This is where we're pulling apart Antarctica and breaking it up. And once we break up Antarctica, the planet will go back to its normal wet, warm, greenhouse climate with sea level considerably higher than now.
Do you think that there is a lot of both coal and oil under the ice in Antarctica?
Oh, yes. I mean, we've got Permian coal deposits there. These are the big coal deposits in the southern hemisphere. These coals are low ash, low sulfur, high calorific value. We know they're there. We've got them in outcrop. The second thing is associated with those coals are oil shales. And these are where we've had lagoons enriched in pollen and spores. These are broken down to give us oil. This has been extracted. These type of canal coals or oil shales are well known globally. And we would expect with that also to form petroleum, which would migrate from those rocks into younger rocks. So, of course, we have resources of fossil fuels in Antarctica. At this stage globally, mining is not allowed in Antarctica, but maybe in 500 years' time, if resources get fairly slim, then we might find a nation state starts to mine in Antarctica. Who knows?
Somewhere in the book, I believe it says that there was a lot of methane in the atmosphere, maybe 4 billion years ago or many billion years ago, several. So we can't call methane a fossil fuel. That methane did not come from life, I guess?
No, we have had in the past a number of atmospheres. Our first atmosphere was rich in hydrogen, helium, methane, carbon dioxide. The second atmosphere, and that was for about 80% of the time, was rich in carbon dioxide, up to 1,000 times more than now. And the third atmosphere now is rich in oxygen. So we've had an atmosphere that's been very rich in methane. We have a lot of methane that leaks out of the planet. This is inorganic. It's not related to any biological process. We know that from the chemical fingerprints. We know that we have methane bubbling out from mid-ocean ridges, from the hot springs and from the volcanoes. We know we have methane leaking out deep in mines. I've been underground and you hear methane hissing out of the rock. And you just pray that no one lights a cigarette because there would be a decent explosion. So most of the world's methane that is produced today is actually of biological origin. Most of it comes from vegetation decomposition, especially in the tundra. A lot of it comes from termites and other animals. Very, very little that comes from cattle. We also have some inorganic methane, but over time, the proportion of inorganic methane has decreased, principally because it's a small molecule and most of it leaked out in earlier times when the planet was much hotter.
Okay, stepping back more and looking at the big picture, I was pleased in the book that there's references to the work of, for solar stuff, for Svensmark and Nersheviv and Zarkova as well. How close do you think we are to figuring out what's going on with a solar effect on Earth's climate? Think we understand it well yet or no?
I think that's an incredibly perceptive question. These are outcasts. Nersheviv in the Hebrew University of Jerusalem, Svensmark in Denmark, and I've forgotten the other one.
Zarkova.
She's up in Northumbria University in England. Yeah. These people are leading edge physicists who are combining physics with isotope geochemistry, with astronomy, and coming up with some ideas which are suggesting the bleeding obvious. And that is that great ball of heat in the sky, which we call the sun, drives climate. Now, if we change the amount of energy coming out from that great ball of heat, we will change the climate on planet Earth. And what they are saying is this is exactly what we've observed in the past. And in the case of Sarkova, this is exactly what her physics is suggesting will be happening in the future, where we have these grand solar minima and grand solar maxima. And she's arguing that we're coming into a grand solar minimum, and this will probably last until 2053. So this is, like geology, one of the great ignored areas of climate science. Climate science basically is inhabited by mathematicians and physicists who are looking at the physics of the atmosphere. They're not looking at what's happening in Earth's history, and they're not looking at what's happening in the sun. And this is why we're getting these scary conclusions which are unrelated to reality.
Yeah, it does seem like even on Twitter, I'm seeing people that they think if they have studied atmospheric physics, that's it. Then they understand Earth's climate. I see I don't think they've looked at anything else other than that. So that amazes me that.
I was reading something yesterday while I was sitting outside in the summer sun next to the pool about the thermal maximum that occurred about 55 million years ago. And there's some strong suggestions that this thermal maximum was actually driven by volcanoes in Iceland. So how can you possibly understand the atmosphere unless you look at other factors, like volcanoes, like the sun, like where we sit in the galaxy, like the Earth's orbit? How can you possibly get anywhere near a valid conclusion? And this is where I think a lot of people who are probably eminently unemployable and have relabeled themselves as climate scientists, and they sit in institutions driving computers and they put garbage into those computers.
Do you have any personal ideas on what the climate is going to do next between now and 2050 or 2100, or do we have to wait and see?
Well, I won't be around to wait and see. In 2050, I think I'll be pushing up daisies. However, the evidence is suggesting that we are approaching a grand solar minimum. We are in a 50 million year cooling cycle, and that continues. We have just come out of the peak of an interglacial and are now going into an orbitally driven cooling. So there are three factors that suggest that we are entering cooling. Now, contrary to previous coolings, we now have double glazing or triple glazing. We have heating. We have international trade. So if you live at a pole, you can actually have food transported to you. The effect of another glaciation will not be nearly as severe on humans as previous glaciations. However, in the temperate zones, in the previous glaciations, we had very strong wind. It was very dry. We didn't have precipitation. We didn't have soils. And so the food stocks might decrease if we actually have cooling down. So I'd prefer to wait and see, but I'm fascinated by looking at the astronomical evidence, the geological evidence, and the evidence that we have from the isotope chemistry.
You think there's any smart stuff we should be doing to prepare in case Yellowstone blows, or in case we get huge surprises in weather? Should we be doing anything to prepare for that, just in case?
Well, if Yellowstone blows, that would create huge problems in Canada and the US. That would create huge problems in the Northern Hemisphere. You may well have what we have in Australia when we get Tongan or Chilean volcanoes erupt, that we get periods of rain bombs where we get massive torrential rain, which strips our soils, destroys our crops. So if you get a massive volcano at Yellowstone, it would have a profound effect on the US. It could actually have such an effect that there would be a shortage of food. The US would survive. It's a wealthy country. It's a country with great innovation, and it's a country with great drive. But the same could be said of Japan. The same could be said of many of the South American countries. We've seen parts of the world wiped out in the past by volcanoes. And I go back and mention again the wiping out of the Minoan Empire. One volcano, Santorini, did this. And it wasn't a very big volcano. It wasn't a super volcano. If you had a super volcano in Yellowstone, I think would create huge problems for the US, but also the rest of the world, because this would the dust would orbit the planet and keep orbiting for many, many laps.
I'm just checking here. Is it for sure? Do we know for sure what caused the younger Dryas? That change?
There are a number of theories. For the listeners, the younger Dryas was a period during the current interglacial. We were warming up. We'd had massive ice sheets, which were over Chicago, a few kilometres thick, over New York, a couple of kilometres thick, over Scandinavia, 5 kilometres thick. And these ice sheets started to break up about 14,500 years ago. This was probably driven by the Earth's orbit. And as they broke up, we ended up having massive armadas of icebergs hit the oceans. Now, nearly 12,000 years ago, we had the ice sheet on Canada break up and drop into the Atlantic Ocean. And what this meant was that the surface waters of the Atlantic Ocean were cool and had a lot of ice and was fresh water, and the water beneath that was warmer and more saline. And it wasn't until we had enough mixing where we had a temperature inversion. That took about 1,500 years. So that's one of the theories. It was a massive collapse of the ice sheet on Canada into the Atlantic Ocean. Another theory is an astronomical theory, and this is related to an impact that may well have hit an ice sheet and pushed that ice into the oceans, and the same effect. And we see that sudden scouring of the land in parts of North America, the Badlands, where you've had a massive scouring with huge amounts of meltwater. So there are a number of theories, but what is interesting about the younger Dryas is it wasn't the only period where it suddenly got cold and then it warmed up, and it warmed up 10 degrees or so over about 10 years. I mean, that's real global warming. We had another period of about 500 years of very, very cold periods some 7,000 years ago. And this is where the population of what is now Turkey moved from the Anatolian highlands into the Black Sea basin. And so we've got periods of time where it has been exceptionally cold. And what people have done is adapt or migrate. Now, with the younger Dryas, our adaptation was to huddle into villages. We created villages. These villages were under attack, so they were fortified. We also started to grow grain and collected grass seeds and grow these as grain. We also mustered our docile animals and had these as animal husbandry, as livestock. So the younger Dryas was a very important period for the advance of humans at the start of agriculture and the start of animal husbandry. So we're not quite sure how it happened. Like most of these phenomena in the past, there are a number of competing theories, but we know that as a result, we humans benefited from that very cold period.
So you mentioned that we've had abrupt warming and coolings even since humans have been on Earth, but I constantly hear this argument that, oh, the warming since 1850 is so abrupt, it's 100 times faster than ever before. But that is just completely wrong. Couldn't be more wrong, could it?
No, it's completely wrong. It's promulgated to scare you. It's got nothing to do with the facts, and it's got nothing to do with the past. And that implies that we are living on a planet that was had actually no climate change up until we sinful humans came along. And that's just demonstrably wrong.
What do you think of the actual CO2 cycle, or do we understand what percent of the CO2, if we believe it's gone up from 280 to maybe 425, what percent of that change was due to humans, and what percent of that may have been natural?
I don't think we understand that well enough. I would argue that our measuring techniques leave a bit to be desired. The former techniques where we looked at bucket chemistry in Europe, in industrial cities, and measuring the carbon dioxide content. Some cities had a carbon dioxide content much lower than today. Some of them had a carbon dioxide content much higher than today. Once we changed the measuring technique and we didn't have an overlap of these techniques, which of course makes my scientific mind very suspicious, we started to have a gradual increase in carbon dioxide. And I get very weary of these gradual curves rather than having spikes of a massive increase in carbon dioxide or spikes of a decrease in carbon dioxide. So the first problem I have with carbon dioxide is the measuring technique. The second thing is that we humans can live in a very high carbon dioxide rich atmosphere. We know that from submariners. We know that if you're in a room of 300 people, the carbon dioxide content is 3 times what it is normally outside. So carbon dioxide is much maligned. We understand the carbon cycle fairly well, but we don't really understand carbon from the deep earth, that we get a lot of release of carbon as carbon dioxide and as methane from deep in the earth. We see some volcanoes, especially where we're pulling apart the planet. These volcanoes are composed of carbonate rock. That's got 44 to 48% carbon dioxide in it, depending upon the carbonate mineral. So the planet has been degassing for a very long period of time. And 2 of the gases are carbon-rich gases like methane and carbon dioxide. We're continuing to degas. So when we're looking at the carbon cycle, it's very hard to understand and quantify the carbon cycle because a large amount of the measurement of degassing, which occurs on the ocean floor, we just can't get to and measure. So we have carbon that does the rounds. We get carbon stored in limestones. We get carbon stored in soils. We get carbon stored in life. And that carbon goes back into the atmosphere upon the decomposition of life or the burning of fossil life material like coal. And in effect, we're looking at things from a very narrow perspective. Another perspective might be that fossil fuels, such as coal is actually fossilized sunlight. And that energy is compressed into a very small volume. Therefore, it's very efficient to burn coal and put carbon dioxide back into the atmosphere where it came from. And if we listen to Patrick Moore, one of the founders of Greenpeace, he argues that that is the moral thing to do because we have been decreasing in atmospheric carbon dioxide over a long period of time, and I'm talking about 500 million years, and we have seen an evolutionary change during that decrease where we had C3 plants evolve, things like sugarcane or corn, and we are now very, very low in atmospheric carbon dioxide. If we halved it, we would probably destroy plant life on Earth. So Patrick Moore is arguing we should be putting carbon dioxide back to where it came from, and that's in the atmosphere. Feed the plant. Don't hug a plant. Feed it.
I agree. Other than the people we've mentioned already, are you a fan of anyone else's work or anybody that's working on stuff that particularly interests you?
Well, I read very, very widely. I'm a fan of many, many people, including atmospheric physicists like Richard Lindzen. So I'm fascinated by the links to the past that we can get by looking at bombarding the planet with radiation, which is what Svensmark's talking about, by looking at the end result of that radiation bombardment, which is what, say, Nir Shaviv is looking at. And I'm hoping to meet Dr. Shaviv fairly soon in Israel, and looking at what the sun does. And by exploring the sun, we are going to the absolute basics of science, the basics of solar physics and the basics of climate. And we have probes now looking at the sun and getting very close to the sun. And I think that's very exciting. So I don't have a particular fan, I read widely, and I will read material and say, oh, that's interesting. I wonder how it relates to this or that. And curiosity is what drives science. It's not propaganda.
So I'm curious, are you following what's going on politically in Australia? Are there certain politicians that seem to be getting it now or speaking out more? Anything like that?
In 2024, we had more than 100 elections in various countries. There were probably 3 or 4 in major countries, including the US and the UK. And 2025, we will have elections in Australia, federal elections, and also one state election. And I think there's a very significant change that's happening in the world. I think there's a rise of conservatism. I think a lot of the younger people, being young, you tend to be rebellious. And by following the authoritarianism of the left, that's not being rebellious. Whereas by following conservatism, you are being rebellious. And so I think we're seeing a shift of some young people into conservatism. I think 2025 will be one of the most politically exciting times in my voting life. After the 20th of January in the US, I think you just got to hang on to your hat. I think it's going to be very, very exciting. We have elections coming up in Australia. We have elections coming up in Germany. These will have a major effect on the way in which we waste public money on frightening people witless about climate.
Excellent. Yeah, I think you're right. I do agree that I think this is a good time to be a conservative. Any other points you'd like to make before we finish up?
Well, no. I'm this morning was planning my trip to the US for the 20th of January. I hope to be both in Washington and in Florida. But I missed out on the 5th of November. I was a bit ill then, but I had an invitation for Florida. And so I'm really looking forward to being part of what I think is a change that will have an effect on the whole world. Now, I'm only talking about climate. Other matters such as the Middle East and China and the economy and inflation, etc., are all very interesting. But I think one of the first executive moves that Mr. Trump will make will be to get out of Paris, and the rest of the world will have to make a decision. Are we going to be uncompetitive, or are we going to follow logic and follow the US? So I think we are facing some fabulously exciting times. We may well have a conservative government appear federally in Australia. The chances are getting better and better each week. We have a socialist government, and socialists are great at spending someone else's money. And it's now becoming very expensive for people in this country. So maybe we'll have a change here also. So I'm very much looking forward to 2025.
So do you plan to do any public speaking when you are in the US or no?
Well, I'm basically going to party. I have to be in Saudi for a few days beforehand. I've got to record a lot of material in the UK on the way through to Washington. The last public speaking I did was in Dublin. I went there and it was with a charming group of people, and they were engineers and scientists. These are people who know their stuff. And I really like public speaking because people question you, and it's the questions that I find very exciting. So on this trip, no, it's a fairly short trip because I've got a few other engagements in late January in Australia and in February. So I shall just go over to party.
All right. I'm glad you're coming over. We'll be honored to have you here. So our time is up here, I think, but thank you very much for doing this and for all the other stuff you're doing. It's so important. I appreciate it.
And thank you for having me yet again.
We'll talk to you next time, Ian Plimer. Goodbye.
Bye.